we are going to move. I don't know why this is not the beginning. We are going to move straight to electricity because on Wednesday we'll review physics, and then on Friday I believe we have the exam on physics, and then next week we'll start chemistry. And like I said, I don't want to shortchange another topic because I covered physics too much. Yes.
You're not writing magnetism?
We're probably only going to get to this for our last dose in physics. So we're going to talk about electricity and electric charge today. And you can see all of these fun things. We start off with, we've learned about forces. What are forces?
Anything that pushes or pulls.
Anything that pushes or pulls. Right, that's a really vital concept to have in your mind. Force is anything that pushes or pulls. I'm sorry to see you swing.
Don't even ask.
Okay, we'll move on then. So how do we know forces exist? Because those are things that we can see or experience. You know, we can feel gravity pulling us down. We can feel the ground pushing us up, and so on. Well, electric force was discovered by seeing something mysterious. So here's an example of seeing something mysterious, assuming I can pull the right things out of the box. So I take this rubber rod. Historically, they used an amber rod, and I rub it with fur, and I really need new fur. This is real fur. It used to be all on one fleece. And they rub it, and this thing here, you see it's all made out of metal. And when I bring it up and touch it, boy, I did a very poor job there. You can see that it moved a little bit, but not a lot. There, it's moving more. And if it made it move, it must have applied a force. And so they said, well, there's something that's causing a force here. There, I did a much better job that time. Something that's causing a force. Now, I said amber was the traditional thing that they used for this. The Greek word for amber is the electron. And so they call this electric force because it was based on the Greek word for amber. And so it's the force that came from the amber. Now, they determined that there were two kinds of charges. Now, when I say charge, you probably already have a good feel for it. But we've talked about gravitational force, and gravitational force has just one kind of charge. What do we call the thing that gravitational force depends on? What property do we measure? Like mass. And so mass is the charge for gravitational force. But with electric force, there's two kinds of charges. So you see, this here, when I bring it closer, it moves it farther away. And I'm going to take a glass rod, and I'm going to rub it on my shirt. I'm supposed to rub it on silk, because I don't have any silk shirts, but we do the best we can here. And if I bring this over, when I bring it close, it goes the other direction. It had the opposite effect. And so they said there are two types of electric charge instead of just one like there is for gravitational force. And so Ben Franklin arbitrarily said, let's call the charge on the amber rod negative. And so it turns out that the extra stuff that's on the amber rods are electrons, once again, named for amber. And so electrons have a negative charge. So electric force is a phenomenon that exists, and we see there are two types of charge. And then, of course, remember on the test, you're going to have the scientific method thing. So let's take that and try to apply it to this situation. We notice something interesting. I rub the amber rod on fur, I bring it up to the metal, and there is a force that makes the second piece push away. And then we have to come up with what's the second step of the scientific method. You first have to observe something interesting. What's the second step? Okay, create a hypothesis that has to do three things. Don't forget those three things on the test. What are the three things the hypothesis has to do? Okay, it has to say why the observation occurred. Just the observation is very important, by the way.
Based on scientific ideas.
Okay, it needs to be based on scientific ideas. It means you have to have some scientific connection, previous knowledge there.
Makes testable predictions.
And it has to make testable predictions. So the scientists, people like Ben Franklin, said, okay, this thing moves, there must be a force, right? That's a scientific idea. There must be a force, and there must be some kind of charge, like mass worked with gravity, to affect this force. And so then they do experiments to test. This is killing me. I bent this somehow. Well, somehow. I'm putting it away poorly. So we need to do tests to see if there are, in fact, some kind of charges that we can learn about, and the process builds up through test after test after test. So as we understand things now, charge comes, we have the two types, so we call one positive and one negative. Thank Ben Franklin for that. You talked about magnetism. Magnetic force also has two charges. And because positive and negative were already taken, we don't use positive and negative for magnetic charges. We call them north and south. So north is a magnetic charge, south is a magnetic charge. And then we have strengths of those. Okay, so the fundamental quantity of electric charge, nobody can tell you where it comes from. All we know is it's innate to materials. And electrons have a negative charge, as per Ben Franklin. Charles Augustin Coulomb did a lot of experimentation, and so based on him, we have a law that tells us about the force. We call that law Coulomb's law, and the charge has units of coulombs. So it's probably on the next slide, but I can put it here anyway. Charge has units of coulombs. Abbreviation C, named after Coulomb, the person who did the experiments to find what the force relationship is. The force law is actually really familiar looking. Well, I take that back, it's not to you. If I taught you the full gravitational force, I don't think I taught you the law for full gravitational force, but gravitational force, the law looks just like this, except for gravitational force. G and K are constants, so you have different constants. M is the gravitational charge, whereas Q is the electric charge, and R is the separation between the centers. So it turns out that the force law, the law that tells us how gravitational force acts, is identical to the force law that tells us how electric force acts. But there is a distinct difference because gravitational force is always attractive. We're each being attracted to everyone else here by gravity. It's a very small force because that constant G is a real small number. So you don't feel everybody pulling on you, but they are. The electric force is generally a much more significant force if you have charged objects. Hence, we see it very readily with this. So K is a bigger number by far. Q is the symbol for charge. We didn't get into it, but Q was the symbol for heat in our last lecture. So you have to be a little flexible with these variables. So the force due to electric charge is charge 1 times charge 2 divided by the separation between them squared, and then of course you do have times the constant K. And for your purposes, K is just a number. I mean, it is just a number, but for your purposes, I'm abbreviating it to just one digit. So that's the value for K. Now, what is distinctly different about this compared to gravitational force is that gravitational force is always attractive, whereas this can be attractive or repulsive. In this case here, when I just had the one rod and I rub it a bit and bring it up here and touch it, I have a force that makes those two pieces of metal move away from each other. It's a repulsive force. What's happening here is I have charge that's spreading over all of the metal. We call metals conductors because charge can move freely. And so we have the same kind of charge on this, and they're pushing apart, which tells us that the same types of charges repel. Now with gravity, we only had one type of charge and it attracted. But with electricity, if we have two charges that are same type, so both positive or both negative, they repel or push away. But if I have a positive and a negative, then they will attract. So opposites attract, likes repel. So that's a distinct difference between the force, the electric force, and the force of gravity. Now, fundamentally, charge only comes in two types. Electrons, and electrons have a charge of minus 1.602 times 10 to the minus 19 coulombs. I should have put that in a different color. I'll do it the right way here for once. There. Electrons come with a charge of minus 1.602 times 10 to the minus 19 coulombs. So you can see that a coulomb must be a really big unit if electrons have such a small fraction of a coulomb. But that's the fundamental charge. And then we have protons. Protons have a charge of plus 1.602 times 10 to the minus 19 coulombs. Notice something cool here. The charge of a proton is positive 1.602 times 10 to the minus 19 coulombs. Charge of an electron is negative that same number. So we define a constant. We define E equals 1.602 times 10 to the minus 19 coulombs. And so a proton's charge is equal to plus E, and electron's charge is equal to minus E. Now, these are all going to be super important as we go into chemistry. Now I always look at Hosanna when I say chemistry because she's already been through chemistry. She can lead us out in chemistry sections. The entirety of chemistry is the electric forces and quantum mechanics, more physics, being applied to atoms. And so it started out under the field of physics, and then it became so vast that it separated into its own field. So, our fundamental rule for electricity, like charges repel, and opposites, or unlike it says here, attract. So if I have a positive charge here, and I have another charge here, what would this charge have to be to make the positive pull out toward it as shown in the picture? I had both answers. Okay, I've got another negative. Negative is correct because I need to have an attractive force. So if this is negative, the force in the positive is going to be like that. The force in the negative is like that. They're both attractive, so they're opposite directions, pulling them toward each other. Now, if instead of putting my charge on that side, if I had put my charge over here, make it bigger, what sign would the charge have to be here to make the positive out the way it is? Now it'd have to be positive because positives are going to repel, which means that this would make a force like that. And, okay, the force arrows should be the same length because Newton's third law says they're going to be equal and opposite, or just the fact that we have the same equation with the same Q1 and Q2. The symmetry says that those forces have to be the same in magnitude but opposite direction. Okay, I'm having a very hard time writing, so I'm going to move it over here so I can fit an arrow on there. So everybody understands two types of charges. What do we call the two types? Okay, protons and electrons works for me. Light is talking about the relationship between the two charges, not the two charges. Positive and negative, and then somebody over here said that too, is the two types of charge. So two positives would be likes, they repel. Two negatives would be likes, they repel. A positive and negative, those would be opposites, and they'll attract. Here is an example of an atom. Everything that we are made of, that everything we interact with, is made up of atoms. I say everything, sure. Electrons, naked electrons do fly through us. Well, we interact with us. Neutrinos fly through us, we don't interact with. There are some other properties or things. Neutrons, of course, are important. And so atoms have three types of particles. They have a nucleus that contains two types: protons, positively charged items, and neutrons. Neutrons are just like protons but have zero charge. They don't interact via the electric force. And then orbiting that, we have electrons. Now this picture is real simplistic. This is the kind of picture they showed me in high school chemistry. And for naivety reasons, I believed it. This is not at all what an atom actually looks like. First, an obvious thing that is not in any way intended here to be confusing. The nucleus where you have the protons and neutrons is very small compared to the average position for the electron. So the scale here, to make it so we can indicate there is a nucleus instead of having a dot, has to make the nucleus way too big compared to the size of the atom. Second is, this shows the electrons like the electrons are somehow on this circle. They aren't. We don't even know where the electrons are at any moment. All we can do is we can calculate where they're likely to be found. And the electrons are likely to be found somewhere in a spherically symmetric shape for the lowest energy configuration. And that's why we end up with pictures like this. Yes?
When we get to chemistry, are we going to have to memorize all the different molecular geometry stuff and the different shapes?
The orbitals?
Yeah, that stuff.
I don't think so. It's not like they're hard. An s orbital, when we talk about these orbitals, they're where the electrons are most likely to be found. So an s orbital looks like this. A p orbital just looks like that. And you hardly ever even draw pictures beyond that. You can look them up and they get complicated. Okay, so atoms have two fundamental charges, the electron and the proton, and then they have one other type of particle, the neutron, that has no charge. Atoms are normally neutral. That is, you have the same amount of electrons as you have protons. Now, if you look back at that periodic table in the back of the classroom, it lists different elements. And each one in the top, where does it have? Top right corner, I have to get up here just so I can read it. In the top right corner has an integer. So the first one, H, has 1 in the top right corner. The second one, HE, has 2 in the top right corner. Li 3, Be 4. That's telling you how many protons are in the nucleus. So the charge of the nucleus will be that integer multiplied by E. And then for a neutral atom, you'll have the same number of electrons. So if you have helium with 2 protons in the nucleus, how many electrons should it have? 2. If you have gold with 79 protons in the nucleus, how many electrons should it have? 79, right. It's not a hard calculation there. You can add or take away electrons. We call that ionizing, and that's something for us to talk about after the test. Yeah, already covered that. Oh, I should mention these. For metals, you can actually pull an electron off a metal or add one to, adding one to a problem. Electrons can move fairly easily around the metal, and you can even take them off fairly easily. So it's easy to charge up or discharge a piece of metal because it's called an electrical conductor. Other things, like this tabletop or wood, electrons aren't free to move. It takes a lot of energy to make them move. And so those things we call insulators. Now, it says up here, rubber is a great insulator. You can still add or take away charge from rubber. Both of these things, this actually is, well, it's supposed to be rubber. It's probably nylon. It's not amber or. Both of these are insulators. That means charge can't move freely around on them. But by rubbing them, I was able to transfer charge to and away from them. In all cases of what I was doing, only electrons were involved. The protons aren't free to move. They're stuck. And so I could only add or take electrons away from the materials. Now, it's time to have a little bit of fun just because it's fun and we're doing physics. So this here is called a Van de Graaff generator. And what it has inside is just a little rubber band. Life's tired. You may. I will. And that rubber band is rubbing on different types of material at the top and the bottom. So it's just like what I was doing with these things. The rubber band is having electrons added in one place and taken away at the other. And so the top is building up a big charge because it's basically a conveyor belt that you rub stuff to get electrons onto the belt. You take the belt from the top to the bottom, and bottom to the top, and you deliver the electrons there. You want to get shot? Come on, boy. Now let me turn off the lights. It's just more fun with the lights off. Okay, so now I mean it's annoying. It's not painful. So this is putting off of what we call high voltage.
I gotta feel it from here.
And yeah, it's drawing arcs all the way out there, which means it's, 3,000 volts, let's say. That's happening because there's so much energy built up in that charge. So there's electrical energy. Just like with other things, you have a force that can do work. And so you have energy, the ability to do work. You notice the flickering of the screen there? Because that runs on electricity, this runs on electricity, and they can interact with it. So you can see those little arcs. Those little arcs are caused by electrons going from a place that has more electrons to places with less electrons. You have a lot of electrons, they're going to be repelling everything else, right? So the electrons are pushing all the electrons away. And if I put something here that can receive the electrons, then they'll fly through the air. And when they fly through the air, they energize molecules in the air. Then those molecules in the air drop back down to lower energy, give off light. So the light is coming from molecules in the air, but because of the charge transferring through. Now, this here helps us to illustrate the forces once again with electric charge. So I'm going to, wrong light switches, these ones. I'm going to put my high tins on here. Made out of aluminum. Will aluminum conduct electricity or is it an insulator?
Conduct.
It'll conduct. So when I put this on here, I'm going to have charge spread throughout all of these high tins. What should happen? What will be like charges or unlike charges?
I hope it's like
If it's the same kind of charge, it's going to be like. So what should they do then? Lights repel. We have to. Okay, we're scientists. We predict. If these have light charges, they repel. So what's going to happen? Which plate is pushing down the hardest? The bottom one. Why? Yeah, it has the overload, as we say. It has the weights of the ones above. So which one's pushing down the least? So if we're pushing between all of these plates with the same amount of force, which one is going to come off? Okay, so there we have a prediction. Exactly right. Right, that's how the scientific method is supposed to work. You make a prediction, you test it, and every now and then we actually are right. You always want to be right because there's certain pride, but you're learning if you're right or wrong. That's part of the scientific method. A negative result isn't wasted time, it's just you learn you were wrong. Yes?
If you put it the other way, but it's like you put it like not on top of that,
Does it look like this?
yeah. What did you say?
We can always test that.
I'm just curious because there's no like platform.
There's no what?
Like platform, like it was forming over it, but now it's not.
Okay. The reason I put it that side down was so it would balance.
Oh,
It's actually cooler that way, isn't it? Okay, so we can definitely see the action of like forces repelling each other. Now I have to bend down again. Now, my hair is reasonably short, so you don't see much. If I put my hand on here, look, I'm not getting shocked anymore. Why not? It's because it's coming onto me at such a slow rate, I don't feel it. And it is exactly what Hosanna said. It's a small but constant current. When I take my hand off, it's going to be small bursts of big amount of charge that I feel. But my body is charging up. So if Bryson comes on back up here, your name is Bryson, right?
Yeah.
Because when I looked at the program, it said Bryce.
if you hold his hand, it's kind of shocking.
Okay, so
If you touch him, it's like shocking.
yeah, it's going to shock me. Not very much. Goodness, not enough.
Oh, there it is.
Yeah, it should have done a better job. I'm apparently transferring charge away. I usually actually have wood out here. We stand on the wood. That way, you do build up a nice charge when you shock you. You might have seen cases where people will like get in a row and one person's holding this, they're all holding hands, and then they touch somebody else. That's actually dangerous, so I don't do that. It's dangerous because you're building up so much charge with all of these people that when you just charge it all to one person, the amount of current flowing through each person is behind us to cause them to have heart attack.
Boys did that, and I touched my dog, and she was red.
Yeah, and don't mess with animals. I think I talked about the bad things that come on with scientific inquiry if you're young and naive.
It got him.
That's not good. By the way, you notice this here? There's charge being transferred through the air to this. One of the things we're going to learn in chemistry section is about polar molecules. Things like water is a polar molecule. Polar means that one side of the water molecule is positive, one side is negative. And since one side is positive and one side is negative, you actually will have the polar molecule comes close to this. If this is negative, then which side of the polar molecule is going to be attracted, the positive side or the negative side? This is negative, it's going to attract positive. And so the molecule will rotate so the side that's attracted is facing this. And then you remember that force equation. Got to go back two more. That force equation was proportional to 1 over the separation squared. So if something is closer, the separation is smaller and the force is bigger. So you have a stronger force between the closer one, the attractive one, than you have between this and the farther one. So that means you have a polar molecule like water molecules. They come and they rotate, then they get attracted in and they touch. When they touch, then charge will actually transfer. We call that conduction. And so then the water molecule, say, picks up an electron. Now the water molecule has the same charge as this, and it's repelled away. And so on a humid day, a day where there's a lot of moisture in the air, the water molecules are attracted to this, they touch it, they pick up charge and take it away, and so it discharges. So on a humid day, you can sit there and rub your feet on the carpet all day. You can't come up and shock your friend on the ear. because the water molecules are taking up the charge that you are developing. You're rubbing your shoes on the carpet. That's exactly like me rubbing this on the fur. And so you're building up a charge on your shoes, you're transferring charge from car, and then your body gets charged up and you come and you transfer that to your friend. Doesn't work on a humid day, but on a dry day, winter days are usually dry days because cold air cannot hold much moisture. On a dry day, it works really well. So, that it's not tormenting your friends, it's just plain practical joke. You can do it on a dry day much better than you can on a day that's humid. Let's move on from that. Not talk about stupid people tricks. I've already talked about this thing. When you brush Fido's fur and scrape electrons from it, so if you take electrons away from Fido's fur, what's going to happen to the charge of Fido's fur? It's going to be positive, that's right. Because you had something that initially was neutral. It had the same amount of protons as electrons. If you take electrons away, it still has the same number of protons because the protons can't move. The only way you're getting rid of protons from Fido is if you cut his hair. Or he breathes or spits. Rules. But you're not going to rub protons off unless you take out hair. But you're taking away electrons, so the protons stay the same, the electrons drop, and Fido becomes positively charged. Conservation of charge is a really important law. We've already talked about conservation of a number of things. And we already have a potential test question asking, what does it mean for something to be conserved in physics? So let's remind everyone, what does it mean if charge is conserved? It cannot be created or destroyed. You can move it around, but you can't create it or destroy it. So whenever you charge or discharge something, you're simply transferring charge from one thing to another. Here's the actual Coulomb's law written out. You'll see there's one thing different than what I wrote, and that is changing R squared to D squared. In both cases, it means the same thing. It's the separation between the centers of the charges. Question, Jessica?
Can you go back
Go back to
to
where?
the last slide?
To this one?
Yeah, it's fine. Thank you. I'm good.
Okay. Here's the constants that I already gave you. Good, they got that covered. Differences between gravity and Coulomb's law, I've already covered. Sorry, you want to take pictures. These will be on Moodle and mere moments.
Yeah.
So much effort. Okay. Getting to the idea of polarization again. Polarization is when the charge is not equally or evenly distributed. You have one side that's more positive, one side that's negative. So the picture on top, that's not polarized because it's symmetrical. But then the one below, you see that the center of the negative charge is here, whereas the positive charge is there. That's what we would call polarized, electrically polarized. It's electrically polarized, so this side here behaves more positively, this side here behaves more negatively, because the charge isn't equally distributed in all directions. And that leads us to cool things like what we will see in lab this week, where we will take balloons and we will rub them on our hair, and then we'll stick them to the wall. If I rub the balloon on my hair, what's happening in terms of electric charge? I have my hair, that's fur. I have the rubber. So what's happening with the rubber when I rub rubber on fur? Okay, and the rubber is getting negative, which means my hair is getting positive because I took electrons off of my hair and put it onto the rubber. So now the wall there is something that has electric dipoles in it, probably water. And so when we bring those and put them up against the wall, The water molecules, now they can't move, right? They're stuck. But they can still rotate. And so they'll rotate so the side that is positive is closer to the balloon, the side that's negative is farther away. And then because things that are closer have a stronger force, there's a net attractive charge. So we can take the balloon and stick it to the wall. And you might see this all kinds of times, like you're taking clothes out of the dryer and they stick to your hand. And what do you say is causing them to stick to your hand? Okay. When I was a kid, we just said static. I didn't even know it was electricity per se. I just knew it was static. But now we can understand that the static electricity, there was charge on those clothes because the clothes have been rubbing in that dryer for a while. And you're basically rubbing electrons between the drum of the dryer and your clothes, transferring them to give the clothes a charge. And then you put your hand in there and you have a lot of water in your body. And so the water in your body is acting like the wall here so that it orients and attracts. And it can be really annoying sometimes. But now you can understand why it occurs. It's because of this new force that's happening between electric charge. Can't see the electric charge, but we can sure see how it acts. Electric fields. I can't believe I'm talking. I'm going to skip over electric fields. It's going to confuse you more than it's worth anything. We didn't do this.
Yeah,
well, for one, I'd have to bring out the wood for us to stand on, because you're definitely not going to have the charge. We can go ahead and anyone want to stand? Anyone? Okay, Bryson, your hair is probably not going to work so well for this.
Yeah, I already did it.
Anyone want me to bring out some wood planks so you can stand on that and see how it doesn't put out a huge amount of voltage, so it's never going to be like hers. She knows the size of her van gap generator is much bigger.
I'll do it.
Okay, so I'll get some wood and we'll have you stand on there and see if you can actually get your hair to move. The wood is an insulator, so charge won't easily go between your feet and the ground. My shoes, of course, have very thin soles, which made it so much easier for me to drain charge. No. Just come on up. And to keep you from getting shocked at all, I'm just going to have you touch that before I even plug it in. Then you won't even get a shock. Okay. So now charge is starting to transfer onto your body. And it takes a little while for the charge to transfer. Like I said, we don't have nearly as much charge to transfer as is going on there, so it's not going to be as significant. If you look at her hair, you can see that there's, the most noticeable thing is on this side where it's sticking out a little. It's starting to lift a little. If I come close, often I can, you can see my hand interacting with it to affect it. We'll let her stand there for a minute or so just to see if anything cool will happen with her hair. Another reason I don't like to do it is you need a much stronger Van de Graaff generator to make it so it's exciting. While she's doing this, I am going to continue and talk about energy. Because opposites attract, if I take an electron and I pull it away from a positive charge, there's more work that can be done. So it's more potential energy. If I let go, it's going to fall back in. Okay, so you guys see, can you see the hair right here that's sticking out? Yes? That's probably about as good as we're going to get her. You can see on this side of her head the hair sticking out. I'm sorry, it's not super dramatic. That's what we got. Now, if she touches me, you will shock me.
Will I get shocked?
Yes.
I don't want to get shocked. Oh, that's funny.
Okay. Actually, look at her hair when that happens.
No.
You see her hair? because she suddenly had a drop in charge, so the repulsion between the individual pairs became smaller because the charge dropped, so they came down. Then it built back up. Okay, it's not good anymore. So we have potential energy with electric charge. And we use that all the time. When we talk about the electricity coming out of the wall, we talk about it in volts. A volt is a measurement of the potential energy per charge. So if something has 100 volts, what's the unit of energy? What's the unit of energy?
What do you mean, like joules?
Yes, joules. That's right. And then something new for today, what's the unit of charge? Coulomb. And so voltage is energy per charge or joules per coulomb. And it occurs because if you have positive charge and negative charge, when they're close together, it's lower potential energy. Farther apart, it's higher potential energy. And so voltage is measuring the potential energy difference in the case of the power coming out of the wall between one prong and the other prong. And so one of them is going to have positive charge and one has negative charge. And the potential energy difference between those is, and when we say it's 120 volts, we mean it's going between plus 170 volts and minus 170 volts, but that's a different thing. Question?
What is the word between
Therefore and joules over.
Units of.
and what's the dot thing? Therefore. Therefore.
There, units. Yes, the 3 dots means therefore.
So this
Sorry.
is the units for voltage.
Yeah, so 1 volt is equal to 1 joule per coulomb. So when we talk about voltage, now it actually can make some sense. It's the energy the charge has in our electric wires. And so, well, we don't need that. We don't need that either. Batteries and generators are things that will give energy to charge. We usually talk about an analogy with water. We treat a water molecule as the charge. And if you raise the elevation of the water molecule, it's going to have more potential energy, right? Because potential energy from gravity was mgh. So you raise it up to higher h, you have a higher potential energy. It's the same thing with a battery and electric charge. You have charge go through a battery, and it's the same as pumping water up to the top of a tower. Remember we had the water tower thing? The battery is pumping the energy of the electron up. And then when you release it, the water would go down through a pipe if there is a pathway for it to go through the pipe. The electron will come down through a wire because the wire is the pathway for the charge to travel. And so the water analogy is very, very apt and makes it kind of easy to visualize. The battery is like a pump that pumps water up to high elevation. The elevation is like voltage because voltage is potential energy per charge, and elevation is potential energy per mass. Well, times G, got that constant there. So a battery, same as a pump basically, but for electric force. Generators are just devices that do the same job, but they're mechanical rather than batteries are chemical. Batteries are chemical reactions. Generators, you put in mechanical energy, like you make it rotate, and that's what gives the energy to the charge. So here is the actual word.
2 seconds.
What was that?
Can you go back 2 seconds?
The actual word for voltage is electric potential. That's the actual, word, that's 2 words. Those are the actual words for voltage. And the units of electric potential are volts, and that's why we call it voltage, because we just say what its units are. So almost never do you hear people in everyday life say, Oh, I would like a battery with a 12-volt electric potential, please. That would be the accurate way of saying it. Instead, they just say, I want a 12-volt battery. It has a voltage of 12 volts, and they go on. Well, you can actually calculate that by the distance of the arc. So you have I think it's 3,000 volts per millimeter for the arc. So if you're able to pull an arc, let's say, of about 3 centimeters, that'd be 30 millimeters. 30 times 30 is 900,000 volts. It seems like I might have the number wrong. It's 90,000 volts. Yeah, it's 3,000 volts per millimeter multiplied by 30, 90,000 volts, roughly speaking.
That's a lot more than a battery.
Oh yes. A battery, you can never get a shock from
You couldn't even feel the battery.
Right, you can't feel the battery at all. And so that brings us to another topic, which, there's the water analogy, which is the rate at which the charge flows. We call that current. So current is how much charge per second passes. And the unit for current, charge per second, coulombs per second. And a coulomb per second, we give a common name of amp, short for ampere in English. And we feel electricity in our bodies because our bodies run on electricity. And if you get a current up to 1 milliamp, that's 1/1000th of a coulomb per second, it's enough for you to feel it. So you feel a shock. If you get up to about 10 milliamps, then you have enough current to make your muscles work. And so if you get 10 milliamps going across your bicep muscle, it will contract without you telling it to. Because the electrical signal is doing what your brain's supposed to be doing, setting the voltage. So above 10 milliamps will actually cause your muscles to contract involuntarily. Now remember, milliamps, that's how quickly it's flowing. The current is the number of coulombs per second. Yes?
He did that in A&P.
Excuse me?
He did that in A&P. He put on
With the
that-
dead frog? Oh, well, it did on you. Yeah. If you go to like your chiropractor, they'll charge you some money to connect you up to these two electrodes they call E-stim, electrical stimulation, and they make your muscles twitch by putting currents through them.
You go on your back.
Yeah.
Yeah, you want this.
And if you get up to about, let's say the ballpark is 70 milliamps going across the heart, that'll make the heart start to behave erratically, cause fibrillations. That's bad, that will kill you. Now, if somebody is having a heart attack, one of the things they do is they put the little paddles on them and they shock them. Now I just said you get up to 70 milliamps and you can cause a person to have a heart attack. So why would you shock somebody's heart if it can cause a heart attack?
Because if it stops, you gotta get it going again.
Your answer is actually the right one, but I think you bet the wrong thing. So, okay, if you're dying, what's the issue, right? If it can help you, let's do it, even if it can also harm you.
Well,
Because
you
it's better.
don't shock someone's heart if it's still going. Because it'll stop it.
Actually, yes, when you shock it, the goal of shocking the heart is to stop it. And if you stop it, it might start up on its own. That's why we shock somebody. We want to get enough current to stop the heart. So 70 milliamps or so will cause the heart to just go into fibrillations. You have the heart as a big muscle. Electric charge should go from the SA node to the AV node. And in doing so, it's going through the atria, making those muscles contract, pumping blood from the atria into the ventricles. We don't have time to go through all of the biology here. But then you have the AV node should send its signal down, and then it comes up through the Purkinje fibers into the ventricles, and that electrical current in the ventricles makes them pump. You get 70 milliamps or so, it's going to cause the currents in the heart to start doing weird things like going in circles. And as my EMT teacher said, it just makes the heart quiver and jiggle around and no blood gets moved. So if you put a bigger current on there, you get a high enough current, it's like my example with the bicep, the whole heart just tries to pump at once and just, seizes. And then when you relieve that current, then it repolarizes, and hopefully the SA node is sending its signal and it gets normal sinus again. There's only certain rhythms, by the way, that you can shock. You don't shock somebody who is in, well, like asystole. Asystole is the heart is not beating. What good are you going to do to try to stop a heart that's not doing anything? Now, in the hospital setting, they have some other things, but in the field, you just don't try to shock that. Okay, so we're out of time. See you on Wednesday. And I will have lots of great updates coming this afternoon.